Hi everyone, and welcome to today's Physics Daily Booster. This is number 13 in our series, and it is an advanced information listed topic for both foundation and higher tier physics folks. The first thing we need to consider then is what happens when current flows through a circuit. As we said in our previous booster, then current depends upon the potential difference. So you've got to have potential difference to have current flow. But that's not the full picture. In addition to potential difference, we also have resistance, which will affect the current that flows in a circuit. We're going to have a little bit of a closer look at resistance then. Now, first thing, resistance is measured in the units of ohms, which has that weird like alien head shape symbol to it. It's actually a Greek letter, but it looks kind of like an alien. Now, what we find here is current is a dependent variable. That just tells us that the only way we can change the current is by changing either the potential difference or the resistance. You can't change the current directly. You've got to change either potential difference or resistance in order to change our current. We do have a calculation here, so potential difference is current times resistance, or V equals IR. This is a really good one to remember because it's going to come up time and time again. Now, I know it looks weird with an I there. You might be thinking, what on earth is I? That is our shorthand way of writing current because C was already used. Now, as far as Ohm's law goes, this is like the go-to for resistance. Ohm's law tells us that current is proportional to the potential difference if temperature does not change. So what that means is that if we increase the potential difference, we increase the current. So bit more detail, if we double potential difference, double the current. So because it is proportional, that means we get that link between the two. Nice bit of a link here with our chemistry from paper 1 knowledge. Hopefully we all knew this. That when we're looking at the structure of metal, what we have is the little picture on the left there. So we've got these positive metal ions arranged in that very nice regular pattern, all nicely touching. And then in between them, we've got those little red dots, which are our delocalized electrons. Remember, a delocalized electron is one that's been freed from the outer shell of that metal itself. Hence why the metals are positive ions and we have delocalized electrons. The key thing about those electrons is they are free to move through the structure. Now, as we said previously, current is the flow of these charged particles, the electrons. Therefore, the movement of those delocalized electrons is what gives us our current. What we mean by resistance is basically something that's going to impede or potentially slow down the flow of those electrons through the structure. Now, one of the key things that's going to happen here is those little electrons are going to collide with the metal ions. Every time they collide with a metal ion, then we have resistance. You should have done an investigation into different factors that affect resistance. And one of the most common one is that you'd have used different thicknesses of wire. Now, ordinarily what we see here is that you've got bits of wire that are stuck onto a meter ruler. You then connect that into your circuit using crocodile clips, obviously attached onto the rest of your circuit with your ammeter, your voltmeter, etc. And what we're then going to do is see how changing the thickness of the wire affects the resistance, because we can measure our current, we can measure the potential difference, and then we can just use V equals IR in order to calculate the resistance of each one. If we wanted to investigate the length of the wire, rather than obviously changing to different thicknesses, all we do is have a single piece of wire on a meter stick, connect your two croc clips about 10 centimeters apart first time, take your readings. Then go to 20 centimeters, take your readings, and so on all the way along. In terms of some of the things to be aware of here, when we do this experiment, then we are going to have some heating of the wire, because as we have resistance being generated, then that leads to heat being created there. So we do need to be mindful of the fact that the temperature is changing, and therefore you should allow a certain period of time between each of those readings so the wire cools down again. Otherwise, we're changing temperature and length, or temperature and the thickness. So just be mindful of that side of things. In terms of a device that we can use to change resistance, then we use these in a lot of everyday appliances. If you've got a dimmer switch in your house on your lights, then that is a variable resistor. And what it does is, if we look at the little picture on the right, this one here, what we can see is this is our basic setup of a dimmer switch. So you can see one of the connections goes to this central part here, and then the slider itself is in contact with this little coil of resistance wire. Now obviously what you're doing is you twist the little dial on your dimmer switch, is that little slider bar is going to be moving either this way or that way, which means we're changing the amount of the resistance wire it has to flow through in order to actually complete the circuit. So obviously you can see this is our other little power supply connection here. So if we had our slider bar up at this point, it would only have a very limited resistance because it's only a short bit of the resistance wire there. However, if we were to have moved our little slider all the way around to the other side, so if we were to have it all the way over here, it's got to travel through all of that resistance wire. Therefore there's a greater resistance, which means the lights are going to be dimmer. What do we do with this stuff then? Well, we plot these things called characteristic graphs. And quite simply, a characteristic graph just has a plot of current against potential difference. So in order to do this, obviously, we need to measure the current flowing through a component at different potential differences. That then gives us the points that we are going to plot on the graph. One point you should remember here is if we're trying to get the data to actually plot one of these characteristic graphs, you need to then switch your connection on the battery or your power supply so that we can get both positive and negative values, because we need to go both positive and negative to get a full set of data to plot our graph. Let's look at some of these key ones that we should know then. First one, the linear circuit element. So this is something like a piece of resistance wire or a fixed resistor, something that has a resistance that does not change. It is a linear circuit element because we have this diagonal line that every 1 volt increase in our potential difference, in this case, leads to a 0.1 increase in our current. So nice and straightforward with our linear. Non-linear circuit elements, these are components where the resistance does change. Think about a lamp. This is our most common example. And what we have is this kind of S-shaped graph that you can see in the bottom left. So it's not a nice diagonal line because our resistance is changing under these different conditions. And one of the key reasons here is that as those electrons are colliding with the positive metal ions in the wire, they're then going to be vibrating more. As a result, the wire gets hotter, and that then affects the flow of our electrons. So as a result of that, we've changed the resistance and we get this varying line on the graph. Third circuit component we should know about is the diode. Now, diodes are special because they only let current flow one way. So current will only flow in one direction. It is worth remembering we have just general diodes, and then we also have light emitting diodes, LEDs, that emit light, as the name suggests. What we see in terms of their characteristic graph then is if you look at the negative, then it literally just stays along that baseline because it does not allow the current to flow in the opposite direction. Look at the positive, we see that steep increase there. So your diode is always going to be obvious because on the negative side, then it will just be a flat line. Whereas on the positive side, you get that increase. Fourth type of our characteristic graph we should know about is the thermistor. Now, thermistors are ones that are going to change with temperature. So the resistance of the actual component changes as the temperature changes. And the reason for that is that it's made of a special material called a semiconductor, and it's usually silicon. And that means that when we've got this silicon, it's a semiconductor, which means it doesn't need much energy for the electrons to escape their atoms. Do note our little circuit symbol down here for our thermistor. So resistors are always a rectangle. With the thermistor, it looks like that weird looking tick going through the middle of it. What we find with the thermistor then is as we increase the temperature, then the electrons are going to gain enough energy to escape, and therefore the resistance is going to decrease. So what we can see is the higher the temperature, the lower the resistance. So you get that nice little curved graph there. Another kind of resistor is the light dependent resistor, or LDR. Now this one has different resistance with different light intensities. There's our symbol again. Notice these two little arrows here pointing towards the actual resistor. Still the rectangle, because that's the resistor sign, and the two arrows pointing in represents the light going towards that to affect its resistance. Again, it's made of a semiconductor, so that when the light is absorbed, then it causes electrons to be released, and therefore the current will increase. So here's our little characteristic graph for this one. We've got our light level, and then we've got our resistance. So increasing the light decreases the resistance. Don't forget to join us again tomorrow for our next Physics Daily Booster, and obviously if there are little bits that you want to go over in a bit more detail, you can use the video on the main channel, you could use your revision guide, your class notes, and as always, don't forget, have a little look at some of those OCR past exam papers as well. They're all available on the OCR website, just to get a bit of a feel for the kind of questions that they ask you on this.